Hi there, I'm Seth. In this video, I'm going to talk about how to use the Spearman-Brown prophecy formula. The last video was all about the intuition behind the formula, how to visualize it, and more generally, how reliability is related to test length. In this video, it's all about applications. So we'll start by talking about 3 applications of the formula. Then we'll talk about how to set it up to automatically calculate in Excel and R. Finally, we'll work through a few practice problems. So, applications. First, as we've already discussed, you can use the formula and solve for RXX star. So you can find out what the new estimated reliability would be if you change the test length by some given factor. Second, you could rearrange the formula to solve for n. So you could find out how much you would need to increase or decrease the test length in order to achieve some target level of reliability. It's the exact same formula. I've just rearranged it algebraically so that we're solving for n instead of solving for RXX star. Another cool usage of the formula is it allows us to compare the reliabilities of tests of different lengths. Given what we know about test length and reliability, a longer test could have more reliability just because of its length, not necessarily because the items are so great. You could approach this in multiple ways. One would be, well, imagine that one test is half as long as the other. You could step up the reliability of the shorter test using n equals 2 and plug that into the formula. Or you could step down the reliability of the longer test using n equals 1/2. So that's what this first bullet's getting at. It's saying we could use a scaling factor that would make the two tests equal, and it basically says, well, here's what the reliability would be if they were equal lengths. Alternatively, you could scale both tests down to the level of a single item. For example, let's say a test has 20 items, you could use n equals 1 divided by 20. And if the other test has 40 items, you could use n equals 1 divided by 40. Run them both through the formula, and you're essentially standardizing the test, allowing you to see which has a better reliability when you're just looking at a single item. Now, before we go through examples of these applications, let's first look at how to use these formulas in Excel and R. Let's start in Excel. Now, I've got a lot of fancy stuff going on here because I can't be bothered to write the formula out multiple times, but we could just write the formula. Like, let's use a familiar example. Let's say we want to start with a reliability of 0.5 and then use a scaling factor of 2. So we're expecting it to come out to 0.67. We just write in the formula. We can say this is equal to, let's see, what's the formula? 2 times 0.5, and it's right here if you've forgotten what it is. Here's how you can represent this in Excel. Okay, so the numerator is 2 times 0.5. Then we're dividing by, open parentheses, 1 plus 2 minus 1 times 0.5, close parentheses. It comes out to 0.67. Then what I like about Excel is I don't like to type out those formulas all the time, but I do like to set it up so that I can just change certain values and immediately get different results. So you see how these are automatically updating. So like right here, what you can see is I've got what would happen if the test length were the same, doubled, tripled, quadrupled, multiplied times 100, or if the test length were divided by 2, divided by 3, divided by 4, etc. So right here, this is if the test length were divided by 1,000. That would be a really long test to start with, I guess. But you can see I've just plugged in the formula. I set it to say multiply n times RXX. It's just the formula with those different parts plugged in rather than writing in the values. I just selected the cells like B4 and A3. And I also locked this into place using a $sign before the numeral, so $3. That way, it looks like I wrote a bunch of formulas. I wrote one formula, then I dragged it down. If there's nothing here, you can grab the bottom right corner and just drag it down, and it auto completes. It just keeps the red cell stays locked into place by that $sign, but then the blue one keeps moving down along with the formula. And down here, I could choose a different one. Like, what if I wanted to say 2.5? There you go. 2.5 in and 0.6 RXX, that's what we would come to. So that's how you can do this in Excel. Here is kind of the same thing, just using a bunch of semi-random values that you might want to start out with. Like, let's say you had a reliability of 0.7 and you wanted to increase it to 0.8. What scaling factor would you need? All I did was I used this formula right here. I just plugged in that formula. Make sure to use parentheses on the denominator, or else you're going to get a result that surprises you. But you can see it says, oh, you need 1.71 times as many items or observations in order to increase the reliability from 0.7 to 0.8. So let's just test something we know. What if we started at 0.5? Oops. And we wanted to get to 0.67, which is 2/3, we would need to double the length. So this is how you can set this up in Excel. And I like to have it like this so that at a glance I could see, let's say I have a reliability of 0.6, at a glance I can see, I'd get to 0.75 if we doubled the number of items. I'd get to 0.82 if we tripled. And then of course it's diminishing returns. In order to get up to 0.9, I'd have to have 6 times as many items that are all comparable. So this is the kind of application that I find Excel is useful for, where you set everything up to auto-populate based on whatever input you give it. And let's just test some things out. What if the starting reliability is 0? Nothing happens. If there's no reliability, then it doesn't matter how many of those terrible items you add, it's not going to change. Similarly, if the reliability is perfect, you could have half as many perfect items or 1/3 as many, and you're still going to have a reliability of 1. Okay, that's fun. Now let's look at R. Let's see, what do we want to do in R? So here's our handy formula. Okay, I wrote out some problems. So use the Spearman-Brown formula to find the expected reliability if we start with 0.8 and then we divide the number of items by 4. Okay, so one thing we could do is we could just write this out. So we can say, what would we do? 0.8 times 0.25, which is what 1 divided by 4 is. And then we're going to divide that by 1 plus what's the best? Yeah, 0.25 minus 1 times 0.8. You know what? We could actually do this one in our heads, because sorry, this may be difficult to visualize, but think about that pie chart where it's 80% true score and 20% error. Reducing the test length by 4 means we're going to quadruple the amount of error, which means it's going to become 80 versus 80. So this has to come out to 0.5. But even if that didn't make sense, don't worry about it. We plug it into the formula and we get 0.5. Okay? So this is pretty much the same thing that was going on in Excel, but I'm writing out the code in R. So what this means is if your reliability is 0.8 and you cut away 3/4 of your items, your reliability is expected to drop to 0.5, assuming the ones you chop are comparable to the ones that remain. Let's create a function to do this for us, because this is kind of a pain. You don't want to have to do that more than once. So let's create a function called SBPF, Spearman-Brown Prophecy Formula. Okay, so that is equal to a function with the inputs RXX and in. Okie dokie. Open bracket, open curly bracket, and then we typically like to represent this across multiple lines. That's just kind of how it's commonly done. Now, what do we do? We can say the result is equal to RXX times in divided by, open parentheses, 1 plus in minus 1 times RXX. So all I've done is I've said the result is equal to this. So this function is going to say whatever you plug in for your first argument, it's going to plug in there, and then whatever you plug in for your second argument, which is your scaling factor, it plugs in there and there. So it's this basically says, I've got this formula, you give me the variables, and I'm going to spit out the answer. Well, it will once I say return the result. Okie doke. Oops. We'll come to that in a minute. So now let's see if it works. I just ran this code, and if you don't know how to run code, just highlight all of it and click run. Now let's see. So Spearman-Brown prophecy formula, let's use something, well, let's use 0.8 and then 1/4, just because that should come to 0.5, right? And it does. So this is, once you've entered the function, you don't have to do it again. I can now just, anytime I want to know what the result of this formula would be, I would just be like Spearman-Brown prophecy formula, SBPF, start with 0.5, then double it, goes to 0.67. What if we start with 0.2, oops, 0.2, and then we increase it by 15? What happens? It goes to 0.79. Okay, so there you go. Now let's scroll down a bit. Here is the rearranged version of the formula where we're solving for n. So let's say we start with a reliability of 0.8. We're trying to get up to 0.9. Let's use this formula to find what scaling factor we would need. Let's see. Okay, so the formula would be 0.9. Whoops. 0.9. I'll write the 0 just because it's fun. Times 1 minus 0.8. And this is the formula in case you're forgetting where this is all coming from. And these are the values I'm plugging in. Then we divide that by 0.8. Remember to put this denominator in parentheses or you're going to get a result you did not want to get. 1 minus 0.9. What happens? 2.25. Let's make sure that I did that correctly. Let's say, I'm going to double check in Excel. Let's say we're starting with 0.8 and we want to get to 0.9. Yeah, 2.25. So Excel agrees that that was calculated correctly. Okay, let's create a function to do that for us. I'm going to call it Spearman-Brown prophecy formula.in, SBPF.in. You can call it whatever you want. This is going to be a function that takes RXX, and I don't want, it is possible to depict that a certain way, but I'm just going to call it the target because I don't want to do anything confusing. So we have our existing estimate and our target estimate that we want to get to. Open curly bracket. Okay, so n is going to be equal to the target times 1 minus the reliability divided by, open parentheses, RXX times 1 minus the target. You don't have to memorize any of this, just check the formula. Okay, so we run that code. Now whenever we, oh, whoops, and then I think we're going to want to return in. Yeah. Okay, so now when we say Spearman-Brown prophecy formula.in, let's say, let's do the exact same thing. Let's say we start with 0.8, we want to get to 0.9. So start with 0.8, get to 0.9, make sure to separate those by commas, and it comes out to 2.25. So once again, you can just use this code. Once you've created a function, you can just plug in the values and figure out what you need. Want to get from 0.5 to 0.9? Let's find out. Start with 0.5, get to 0.9. We need 9 times as many items. Okay, now let's walk through some demonstrations. We've got a 30-item test. The reliability is 0.85. Your client wants to cut half of the items, so they want to remove 15 items because they don't want to spend as much. They don't want people spending as much time on the test. What's the expected reliability estimate for the shortened test? Okay, so feel free to pause the video and solve this, whether mentally, visually, by hand, Excel, R, whatever. And I'm assuming that you're now unpausing. We can plug in our reliability of 0.85, and notice because we're going to 30 to 15, that means n equals 1/2, because the original length is getting cut in half. And you see we come to the same answer regardless of which tool we use. So if we chop the items in half, our reliability is going to go down from 0.85 to 0.74. Whether or not that's acceptable to you and your client is a matter of judgment. Let's do another. You've got a 30-item test with a reliability of 0.85. Now your client's saying they want the reliability to be at least 0.9. How many items do you need to add? Go ahead and pause, then solve using your preferred method. Okie dokie, and now I'm assuming You've solved it, so I'm going to unpause, or I'm going to advance. All right, so when we plug it in using whichever type of function we want, we come to n equals 1.59. But there's an additional step here. The question doesn't ask, what's the scaling factor you need? The question says, how many more items do you need? So let's see what 30 times 1.59 becomes. We started with 30, and we need to increase that by a factor of 1.59. We need 47.7 items. Now, 47.7 is not a valid number of items, so we're going to have to round that up to 48. Notice that the number of measurements need to be treated as integers for what we're doing. And this is extremely important for inner rater reliability. Please, please do not cut your raters into halves or thirds just because the formula tells you to. It's extremely painful. Instead, when you get a decimal, just round as appropriate. But you kind of need to think through whether it makes sense to round up or down depending on what you're doing. Okay, so we can't have 47.7 items, but rounding down would not bring us to our target level of reliability. So we're going to round up to 48. That means we had 30, we need to get to 48, so we need 18 new items. And those items need to be comparable to the original 30 items. Okie dokie, last one. Test A is a 25-item test whose reliability is 0.7. Test B is a 50-item test whose reliability is 0.8. So you might think, well, 0.8, that's better than 0.7 probably, assuming we're using a unidimensional scale. But then you might think, wait, this one has more items, so maybe that's the only reason that it has better reliability. Feel free to pause and work out which of these two reliabilities is more impressive. Remember, there are a few different ways you could approach this. Okie dokie, revealing the answer. Because test A is half the length of test B, we can step up the reliability of test A using the Spearman-Brown prophecy formula. So you can see when we plug it in, the reliability comes to 0.82. So you could say 0.7 on a 25-item test is like having a 0.82 on a 50-item test. So test A is more impressive than test B. Or you could go the other way and you could scale test B down, and you would find that it goes to less than 0.7. Alternatively, it's kind of fun sometimes to scale both of them down to the reliability of a single item. So here I scaled 0.7 divided by 1, and the scaling factor is 1/25. Because there are 25 items. So scaling down to a length of one item. And then doing the same here with this 50-item test. And again, the result is the same. You can see the reliability is better for a single item for this first test than for this second one. So the reliability is more impressive for that first test. Now, this second approach can be especially useful if you've got like 10 to 15 different measures of the same construct and you want to put them all on equal footing to see how they stack up against each other. Just reduce all of them down using the Spearman-Brown prophecy formula to the level of a single item and see how they stack up. Anyway, whichever of the three approaches you use, you're going to come to the same conclusion, which is that test A has a more impressive reliability than test B, considering the differing lengths. Okay, that's it for the Spearman-Brown prophecy formula. If you watched both videos, or especially if you watched all three in this series, then you now know more about this formula than you ever wanted to. Let me know if you have any questions or comments. Otherwise, till next time.